Hello, I'm Mervin and I'm currently in the second year of my BTech CSE program. Today we'll be looking at a very interesting sorting algorithm that many of us, or at least I, wasn't aware of. Now I have been using this algorithm unknowingly for such a long time. Now what is the sorting algorithm and how does it function? Let's take a look. Alright, so today we'll be taking a look at an algorithm that was invented not too long back called Timsort. Now, before we go further into the details, let us all take a look at what all we'll be discussing in this video. In this video, we'll learn about Timsort and its history. We'll also be comparing Timsort to other sorting algorithms that we generally use and see why there was a need for an algorithm like Timsort. After that, we'll break down Timsort into steps and understand each one of them one by one. We'll also be taking a look at the time and space complexity of Timsort towards the end of the video. Remember that in this video we will not be talking about the code implementation of Timsort because it is already available in the Python documentation. Timsort and its history. So Timsort was invented in the year 2002 by Tim Peters and has been the default sorting algorithm since version 2.3 in Python. Fun fact, it was Tim Peters who wrote Zen of Python, the 19 guiding principles of writing computer program. Now for those of you who don't know, that is an Easter egg that can be accessed by writing the line import this on your Python line. Anyways, now you might ask why should we use Timsort or what was the need for Timsort? Now see, Timsort isn't an algorithm that was built from scratch. It is actually a hybrid algorithm and it is adaptive in nature. And what do I mean by that? Basically, Timsort uses merge sort and binary insertion sort but in a very efficient way. And because of this, Timsort takes n log n time in the worst case, which is similar to merge sort. Now the plus point of Timsort is that it was designed by keeping in mind the real world data. Now Tim observed that in the real world not all the data is randomly distributed. So there are parts or chunks of data that are already sorted, either in a decreasing or in an increasing manner. So he thought of an approach to exploit these chunks of data called runs in Timsort. Moving on, now let's compare Timsort to other sorting algorithms. Yes, quicksort is fast. It has an average time complexity of n log n, but in the worst case, it takes n squared. It is efficient for large data sets, but not so for small data sets. And in the case of merge sort, although it's efficient and has a time complexity similar to that of Timsort, it uses n spaces extra to store data temporarily. Now mind you, Timsort also has a space complexity of on, but this n is always less than the size of the array, which is not the case in merge sort. The only problem with heap sort is that it has a poor locality of reference. Otherwise, it was also a very efficient and fast algorithm. Okay, so now that you've discussed whens and whys of Timsort, let's move on to the functioning of Timsort and take a look at how does it work. The working of Timsort can be divided into 4 major steps. Okay, the fourth step is not really a step, but it is more of an optimization process in Timsort. In short, under Timsort, first we check the size of the list. Now if it's more than 64 elements, we look for the sorted chunks called runs in the list. And to get the final result, we merge all of these runs together. Now you might think, wow, is that it? Well, it kinda is, but kinda isn't as well. So let's take a look at all of these steps in detail now. Step 1. Checking the size of the list or array. Now, when Timsort is given a data set, it straight away checks for the size of the list or array. Now, you may ask why? Well, it is to check if the size of the list is less than 64 elements or not. Now, if the size of the list is less than 64 elements, we can straight away apply binary insertion sort on it. Now, I know we're discussing Timsort, but it has been noticed that binary insertion sort is the most efficient and fast algorithm for sorting arrays of this size range. But what if the size is more than 64 elements? Well, it's easy. We move on to step 2. Step 2. Finding runs in the list. In Timsort, the sorted chunks of data is called runs or natural runs. The natural runs have a condition where they have to be always sorted either in the increasing or in the decreasing order. Now, why do we look for such runs? Well, it's because we don't have to sort these runs, they're already sorted. So, the algorithm during its first pass looks for such runs, but at the same time, it's also calculating the min run. Now, what is min run? Well, when we find runs, the size of the run can be anything from 2 to n. But if there are a lot of runs of 2 elements, then Timsort won't really be an optimization because it will be exactly same as one sort. So there's a condition. The size of each run should be at least equal to min run. The algorithm chooses the value of min run from the range of 32 to 64 because binary insertion sort has been found to be faster in arrays of this size range like mentioned before. Also, the value of min run is always or generally equal to or less than the power of 2 because merging of lists of such sizes is also found to be the fastest. Now let's take an example. Look at this list. We observe that the first 6 elements, that is element 26, 22, 18, 12, 9, 3 are all in the decreasing order. Now at 6 we find that the order breaks. So the elements from 26 to 3 are all in a decreasing order and they form the first run. Now since at 6 the previous run broke, the second run starts from there and it goes till where it breaks next. So elements 6, 13 and 17 which are in the increasing order become a second run. Similarly, the other runs can be also found in the list. Now note that we didn't take the condition of min run here. We'll do that in the next example. Now let's take another example, and now while finding runs, let's take the rule of min run into consideration. Here we have taken min run equal to 3. Okay, like in the previous example, if we were to find the runs in this list without the condition of min run, it would consist of 2 elements, 8 and 12, because at 9 the order breaks. But there is a condition, remember, of min run. So in order to fulfill that, we add the next element of the list to the run. But now the order has broken. The rule of runs, which is that the run has to be always sorted, has been broken. So in order to fix that, we use binary insertion sort, under which the 9 goes to its correct sorted position in the run. And after that, the original list becomes as such, where the first 3 elements are now in a sorted manner. Now, let's take a look at the next element in the list, which is 17. Now, will we add that to the run? That's a very good question. Because in Timsort, it states that the next element in the list is in the same order as the current run, then the algorithm continues to add that element into the run. So, we add 17 into the run. And the run now becomes of 4 elements. So, the final run or the first run will consist of 4 elements, 8, 9, 12, 17, all in a sorted order. Now, I talked about binary insertion sort and said that we'll come back to it later. Why don't we take a look at how binary insertion sort works? Now, binary insertion sort is similar to insertion sort, but here we use binary search to find the correct position of the unsorted element. Let's take an example. Here we find that the elements from index 0 to 3 are already in a sorted manner. Element 11 or at the index 4 is unsorted. In order to put it at its correct position, it has to move to the left to the sorted section of the list. But in this, we perform a binary search. A normal generic binary search where we use left and right and the mid pointer to find the correct position where 11 should be placed. Now, when we find the correct position, the search stops and 11 is shifted to its correct position and all the elements are shifted one place to the right. Similarly, all of the other elements are also sorted. Alright, now let's come back to our example. Now, the second run, what would it mean? Now, the second run without the condition of min run would consist of 2 elements, 15 and minus 1. But now there's the condition of min run that you have to take into consideration. So we add the next element in the list to the current run. Now the run is no longer sorted. So in order to sort it, we use binary insertion sort. After that, actual array also changes. Remember, we are finding the runs and sorting them in the actual array. So that's why the arrays are also changing. Now if we check if the next element in the list can be added to the current run. Find that it can't because 11 is not less than -1. So if we add 11 to the run, it would become unsorted. So we omit 11 and the second run would be 22, 15 and -1. Similarly, if you were to find the third run, it would consist of elements 11, 10 and 7. Step 3. Merging the sorted runs. Once we have all these sorted runs in the list, we have to merge all of them together. Now, merging two subarrays or runs in this case can be done in a very efficient method. In the case of Timsort, a special type of merge sort is used called in-place merge sort. Now, let's take a look at in-place merge sort with an example. In this example, we find that the elements from 0 to 5 make up our run 1 and that of 6 to 9 make up a second run. And we also notice that the size of run 2 is smaller than run 1. And let's assume the size to be n. Now, what we do is we make a copy of this run and store it in a temporary list. After having done that, we move the first run by that many n places. Remember, we're moving the run 1 in the same list. Now, we check the first element of run 1 with first element of the temporary list. And we find that 3 wins because 3 is less than 12. So, what we do is we move 3 to the first position in the list. Next, we check for an element at index 5 with the first element of the temporary list. We find that 5 wins. We move 5 to the second position of the original list. Now, let's look at the element at index 6. We find that in this case, the first element of the temporary list wins. So we move 12 to the third position of the actual list. Now, in this manner, the merge sort continues and sorts all of these elements into the first list. Now, concept of stacks. Now, as and when the algorithm finds runs in the list, it keeps adding them to a stack. While merging, we only merge the adjacent runs because we want to maintain stability and a merge balance. Now, Timsort has to balance two competing needs during merge sort. On one hand, we would like to delay the merging as long as possible in order to exploit patterns that may come up later. But we would like even more to do merging as soon as possible to exploit the run that the runs found in still. But we would like, there are two laws in the concept of stacks. Step 3, part 2, Galloping. Now, like I mentioned before, this isn't really a step in Timsort, but it is more of an optimization process. While merging two runs, if the algorithm finds that one of the run has been winning for a long time or many times, instead of pushing elements one by one into its correct position in the original list, it can push a whole block. To carry out this process, algorithm uses binary search to look for the position where the chunk can be put. So all in all, a considerable amount of time can be saved through Galloping. Now, I have explained Galloping in much detail in my blog. Time and space complexity. Now, what would the time complexity be? I mean, that's the biggest question. Now, since we're applying binary insertion sort for elements of size 64 and less, the time complexity for its best case would be n log n, and for its average and worst case would be n squared. And for in the case of Timsort, at its best case, it has a time complexity of n, and for its average and worst case, it's n log n. Now, why is that? Well, it's because since binary insertion sort is only employed when it's not harmful to the performance, So the worst case of Timsort will be analogous to that of Mervin, which is n log n. We've looked at the time complexity. Let's take a look at the space complexity. Now, the space complexity of Timsort would be O(n), but this n, like I said, will always be less than the size of the array. Timsort is a very fast and stable sorting algorithm. But more importantly, it is designed with keeping in mind the real world data that is available to us. Now, are there better and faster sorting algorithms? Probably yes. Can Timsort be used at every situation? Maybe not. But in the end, it is an optimization. And learning about algorithms is all about finding an optimal approach to a problem. And with that, I'd like to end my video. Thank you.